Urbanization in low-lying deltas combined with climate change is increasing flood risks globally. Without appropriate measures, this leads to higher death toll and economical losses. Among climate adaptation solutions, the Intergovernmental Panel of Climate Change recommends floating buildings. To date, this solution received only limited attention in research and practice and is therefore the focus of this design study. This study is based on the river floodings in Lismore, Australia of 2021. The method of this study follows the double diamond design process as presented here. In the first part of this video, we define the problem with data collected mostly from on-site observations and interviews. The next part of this video delivers a solution through presentation of the floating building design with a review of how it addresses the problem. Lismore is the location of our study. This small city is located on the east coast of Australia, about 150 kilometers south of Brisbane. Lismore is located in a flood basin and has therefore already a long history of floods. The government and the residents have taken measures to protect itself from these floodings. The three key flood measures are 1. A levee of 10.5 meters around the city centre. 2. Most vital infrastructure functions such as hospitals are placed on the higher grounds on the east side. And 3. The lower suburbs have raised Queenslander stilt-houses. Here in the flood-prone region, they may be raised up to about 5 meters. However, in 2022, torrential rain in the region raised the river considerably, exceeding the height of the levee and most stilt-homes. Not one flood, but 2 floods occurred with just 30 days apart. They were supposed to be once-in-a-100-year events. The first flood peaked at 14.4 meters, surpassing previous records by 2 meters. The second flood peaked at 11.5 meters. The floods flooded the city centre, as the levee was overtopped. Many homes flooded up to the ceiling of the second floor. Over 3,000 homes became inundated. Both flood peaks were also well above the stilts of the elevated Queenslanders. One of our researchers participated in the cleanup afterwards. During the cleanup, the material damage became very apparent. Observations were made and flood victims shared their experiences. 5 types of flood damage were identified. 1. Damage from muddy water inundation. This caused water damage on building materials and inventory, plus a layer of dirt covering everything. In the cleanup, mud was washed out with high-pressure water jets and fans added in the drying process. However, much of the inventory, electric wires and building materials needed to be thrown out. A lot of the timber bended in the drying process. Also, much timber and textile materials quickly developed mold afterwards, particularly in the cavities hidden from sight. 2. Damage from water pressure. Walls bended, cracked and collapsed because of the weight and strong currents of the water on the walls. 3. Damage from debris. Tree trunks, broken homes, containers and other large debris collided into buildings. The debris either floated on top of the water or crawled along the bottom. 4. Looting. During and directly after the flood, some people trespassed into buildings searching for valuables to steal. 5. Human harm. Not everyone responded to the evacuation order. Some people stayed to protect their property and/or expected to be safe on higher floors. Rescue attempts were made during the flood, but not all lives could be saved. The outcomes of the discover and define phases form the input for the develop phase. The damage analysis and Lismore site analysis quickly concluded that the potential for an amphibious floating building will be much larger compared to a permanently floating building. Therefore, an amphibious building was designed in the develop and deliver phases. This design has an open floor plan suitable for various functions, such as multiple apartments, office, retail, public use, or mixed-use design. The shape is rectangular, 22 meters by 10 meters, with 3 floors on top of a semi-submerged basement. The long side has river view, which also means that it is orientated parallel to the flood water direction. The terrain may be on a slope down towards the river. This could give easy access to cars to park in the semi-submerged basement on the back. A building close to the river and accessible without high stairs would provide high functional value, but unsafe for floods if it was not amphibious. The building has two distinct elements, the base and the floor space. The base is made of the basement and two tall side walls with staircases. They are to be from reinforced concrete, as they should be strong to withstand structural damage by water pressure or debris. Also, the concrete or any other material here should be invulnerable from water and easy to clean of any mud. The floor space is made of 3 floors from a lightweight construction system, on top of a pontoon. The pontoon is made from a steel space frame with polystyrene blocks in between. The outside of the pontoon is cladded in corrugated metal to shield the polystyrene. The floor space stands on the basement. During a flood, the floor space can float by sliding upwards between the base side walls. Along the length of the building is a veranda and balustrade that gives access to the ground floor and also protects the glass facade from floating debris. The floor space element needs to be lightweight to float, but this makes it more challenging to avoid damage from water, pressure and debris. However, this is what the base does for the whole building. One side wall faces the incoming water flow from the flooding river. The side wall deflects most of the water pressure and can handle impacts from debris, as it is made from concrete and in a strong shape. The basement also plays a significant role in protecting the floor space from debris. The basement sticks up as a pedestal above the ground, and because of this, crawling debris will bump into here instead of the floor space. The ceiling of the basement is open during a flood, and therefore debris is unlikely to get stuck between the basement and the pontoon. Debris falling into the basement should easily flow out the garage entrance. We believe that this amphibious design can prevent damage from muddy water, water pressure and debris. Damage from looting and human harm was also taken into consideration. The building could be the evacuation place for people nearby. This reduces evacuation distance and time. It also allows to keep sight of nearby buildings, to easier save people from there or to spot looters. We argue that this amphibious building design is a realistic and feasible solution for Lismore, and many relatable cases around the world. Thank you for your attention. Please place your questions on the YouTube comment section or reach out to any one of us.